children, how are you? Doing well? Very good. Dear children, introduction to alkanes. We have completed introduction to alkanes, nomenclature of alkanes, then synthesis of alkanes we have completed. Today we are going to see chemical properties. Under chemical properties, we have completed substitution reactions. In previous video, we have completed substitution reactions. Under substitution reaction, we have completed halogenation, yes, nitration, sulfonation, chlorosulfonation is already completed. Yes, friends. So, under chemical reactions or chemical properties of alkanes, today we are going to learn combustion, controlled oxidation, isomerization, followed by aromatization, then reaction with steam, and conformations. Conformations of alkanes is very important, friends. So in this video you are going to learn these chemical properties or chemical reactions of alkanes: combustion, controlled oxidation, isomerization, aromatization, reaction with steam. Today I am going to complete these things. Let us see combustion. What is combustion? Yes, combustion, it is the amount of heat produced by burning or heating the fuel of 1 kg. Yes, friends. So it is combustion. Right. Anyhow, heat of combustion. Alkanes undergo combustion. For example, alkane, methane. I am taking methane. Methane in presence of oxygen, yes, 2O2 gives rise to carbon dioxide plus H2O. Right, friends? 2H2O. It is the heat of combustion is going to be very high. These compounds will give very high heat of combustions. For example, minus 890 kilojoules per mole. Dear students, so alkanes undergo combustion reaction. So in presence of oxygen, alkanes burn and gives rise to energy. So CH4 2O2. If I take butane C4H10, yes, C4H10, it is going to react with C4H10. 13/2 O2 gives rise to 4CO2 plus 5H2O plus energy. Energy is nothing but how much energy is we are going to get? Yes, minus 2875 kilojoules per mole. We are going to get per mole. We are going to get, right? So methane in presence of oxygen undergoes combustion to be carbon dioxide and water. And if I take butane, in butane, so it uses oxygen. Then how to calculate this? How much oxygen is required? So there is general formula. What is the general formula for alkanes? CnH2n plus 2. This requires, this is alkane general formula, already I explained. CnH2n plus 2 requires 3n plus 1 by 2 oxygen is required. It gives rise to NCO2 plus N plus 1 O2 and the energy will be released, right? So is released. So it is exothermic reaction. Alkanes in presence of oxygen undergoes combustion, gives rise to energy. So this is how we have to calculate. For example, if I take C5, what is it? C5, 5 to the 10 plus 2, 12. C5H12 is nothing but N-pentane. If I burn with oxygen, how much oxygen is required? 5. Means 3 into 5. 3 5 is 15 plus 1 16. 16 by 2 equal to 8 oxygen is required. 8 oxygen is required. So that I will get 5 carbon dioxide, right? So N plus 1 means this is 6 H2O I am going to get plus delta C, that is C stands for combustion. We are going to some energy. Energy will be released. This is how heat of combustion can be calculated, or the amount of oxygen is required for the combustion of alkanes. It is a general formula. Yes, it is a general formula for how much oxygen is required. Very good. Suppose if I use less amount of oxygen, what happens? So this is, since these alkanes, methane, butane, all alkanes gives energy, these are used as fuels. Fuels. Yes friends, so for aeroplanes, alkanes are used as fuels. Even our kerosene, petrol, gasoline, right? Hexane, heptane, these are all used as fuels, right? So even petroleum LPG gas, yes, liquid petroleum gas, or other gases also are alkanes. These are all alkanes we use it for as fuels, right? If I use less amount of oxygen, for example, if I use CH4 plus, here I have taken, right, Cn, based on this equation I have to use how much? C, if it is 1, I have to use 2 oxygen, but if I use only 1 oxygen, that is 1 mole of methane plus 1 mole of oxygen, I will get carbon. I am not going to get carbon dioxide, I am going to get carbon, right? It is a solid, I am going to get carbon plus water, 2H2O. So this carbon is going to be used as ink for printing purpose. I am going to, this carbon is going to be used as ink in printing, right friends? Right students? So this is how alkanes combustion reaction is very important to understand. This is how alkanes undergoes combustion. So for complete combustion, we need this much oxygen. This is incomplete combustion. We can say it as incomplete combustion. Incomplete combustion requires less oxygen, or in presence of 1 mole of oxygen with 1 mole of methane, we are going to get carbon solid. This carbon is used as ink in printing machines. This is what combustion of fuels. So combustion of alkanes, because of this nature of alkanes are used as fuels. Yes friends. Next, controlled oxidation. Controlled oxidation, yes. Is it easy to oxidize alkanes? No. It is very tough to oxidize alkanes. These are unreactive. Alkanes are unreactive to all reagents, but some alkanes undergo some reactions. So controlled oxidation is possible in presence of some catalyst. For example, if I take methane and controlled oxidation, if I control oxidation in presence of copper or some catalyst, Kelvin, and in 100 atmosphere pressure. So this reaction is done in a pressure. I am going to get 2CH3OH. So methanol I am going to get, isn't it? So this is a methanol. It is a very important reaction, friends. How to prepare methanol from alkane? Yes, alkanes, controlled oxidation of alkanes, we are going to get this methanol. For example, the same methane, if I use oxygen, right? So if I do, so in presence of molybdenum trioxide heating, I am going to get CHH. What is this? Just a guess. So what is this compound? What is this? This is formaldehyde. So these are all very important synthetic intermediate, formaldehyde. Methanol and formaldehyde can be prepared by controlled oxidation of methane in presence of catalyst under high pressure and under heating reaction conditions. So methanol we can prepare from this methane and formaldehyde. If I use ethane, CH3 ethane plus oxygen 3O2 in presence of molybdenum estate, manganese estate, sorry, Mn estate. I am going to get CH3 COOH. What is this? CH3 COOH? Yes, ethanoic acid. Ethanoic acid. What is the common name? Ethanoic acid or acetic acid. This is also known as acetic acid. Common name is acetic acid or ethanoic acid. Ethanoic acid or acetic acid. Yes, friends. So methanol, formaldehyde, acetic acid can be prepared from alkanes, methane and ethane. However, further oxidation. For example, we know what is the Bayer's reagent, Bayer's oxidation. Bayer's or oxidation of alkanes using KMnO4. Oxidation of alkanes using KMnO4. This is Bayer's reagent. Bayer's reagent in presence of base is Bayer's reagent, but we are going to use only KMnO4. Right, friends? So oxidation of KMnO4, oxidation of alkanes using KMnO4. Usually alkanes do not undergo oxidation. No, oxidation is not going to take place using KMnO4. However, tertiary alkanes gives rise to KMnO4. In presence of KMnO4, heating gives rise to tertiary alcohols. For example, if I take this is alkane, CH3. What is this? What is the common name? Yes, 2-methyl propane. 1, 2, 3. Right? 2-methyl propane in presence of KMnO4 gives rise to 2-methyl propane to all. 2-methyl propane to all. This is 2-methyl propane to all. I am going to get, this is the oxidation. It is controlled oxidation. This, what is the common name? Tertiary butanol. It is also known as tertiary butanol. Dear friends, dear students, dear children, so under controlled oxidation reaction conditions, alkanes gives oxidized compounds. Usually alkanes do not undergo oxidation that easily. However, in presence of catalyst at high temperature under pressure, it is going to undergo oxidation. For example, methane in presence of oxygen, yes, we get methanol. Or if we do with molybdenum trioxide, we are going to get formaldehyde. For example, if I take ethane and do the oxidation using manganese estate, I am going to get acetic acid. Acetic acid, what is acetic acid? Yes, vinegar. It is nothing but vinegar. Yes, it is a food additive. Yes, vinegar. In place of lemon juice, yes, we use vinegar as a food additive to give taste, sour taste. Yes, as it's a sour in taste. Right. So oxidation with KMnO4, oxidation of alkanes with KMnO4 usually do not undergo, but the alkanes which are having tertiary alkanes which are having tertiary hydrogen, this is tertiary, because this carbon is attached to 3 carbons, 1, 2, 3. So tertiary carbon, or this is the hydrogen having attached to tertiary carbon, is going to undergo this easily replaced with OH. So this is the special reaction of alkanes. We are going to get tertiary alcohols. This is what? Controlled oxidation. Yes, friends. Next word. Yes. Very, very important reaction. Isomerization. What is isomerization? Yes. Isomers can be obtained from higher alkanes to lower alkanes? Yes, isomers are the compounds which are having same molecular formula but structurally different. Structurally different. Yes, isomers are same molecular formula but having different structures. For example, yes, I am going to take N-hexane. N-hexane. What is N-hexane? Yes, CH3, CH2, 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 1, 2, 3, 4, CH2 and CH3. This is N-hexane. N-hexane. And what we are going to learn? Isomerization. Isomerization. That means same molecular formula with different structure. What is the molecular formula? Yes, C6H14. C6H14. This undergoes isomerization in presence of aluminium chloride under heating reaction conditions. Aluminum chloride followed by HCl. Aluminum chloride and HCl. In presence of aluminum chloride and HCl, alkanes undergo isomerization. That means it gives two isomers, further isomers. So it is going to replace, or this is one isomer, CH3, C, methyl. This hydrogen will be there. Hydrogen, CH2, CH2 and CH3. What is this? 1, 2, 3, 4, 5, 6 carbon. So C6. How many hydrogens are there? 3, 2, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. So same molecular formula, but structurally different. These two are isomers. Yes, these two are isomers. So what is this? 2-methyl pentane, 2-methyl pentane, 2-methyl pentane. And it also, how it is going to form? Yes friends, it is very simple. Yes, it is expected. Yes, this is the structure of this hexane. So simply this methane is going to come here, right? So this hydrogen is going to be attached to here. So it is isomerization. It is very simple. Or it can give isomer of 3-methyl pentane also. It is 2. So 3-methyl pentane also can be obtained. Yes. CH2, CH3. 3-methyl pentane. Yes friends. So 2-methyl pentane and 3-methyl pentane is obtained from alkanes. That is from higher homologs of alkanes. It is going to be isomerized to lower chain alkanes. These are chain isomers. Chain isomers. So chain isomers. Yes, isomerism we will learn very soon. So chain isomers are obtained from alkanes. This is 2-methyl pentane. 1, 2, 3, 4, 5. And what is the molecular formula? Yes, C6H14. Same molecular formula. But here, for example, 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. So 3-methyl, 2-methyl. So 2-methyl pentane, 3-methyl pentane. This is hexane. 3 compounds are different, right, friends? So these are isomers. Isomerization of alkanes. Yes. What else? Aromatization. Next, what we are going to learn? Aromatization. What is aromatic compound? Yes, do you have any idea? Yes friends, the compounds which follow Haeckel's rule are going to be aromatic compounds. Yes, the compounds, those which are going to have CN 4n plus 2 pi electrons. These compounds are going to be aromatic compounds very soon. Yes, next after these 2 classes I am going to explain aromatic compounds. Anyhow, so aromatization takes place. Aromatization of alkanes. Yes, so aromatization of alkanes. For example, so to take place aromatization, we need at least 6 carbons. The alkanes which are having 6 or more number of carbons are going to undergo aromatization. Yes, aromatization I am taking hexane. So hexane can be written as like this: CH2, CH3, CH2, CH2, yes, CH2, yes, CH2, CH3. How many carbons are there? 1, 2, 3, 4, 5, 6. This is N-hexane. 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 If I do aromatization in presence of oxidizing agents, these oxidizing agents takes out hydrogens. Oxidizing agents takes out hydrogens. Oxidizing agents, what are the oxidizing agents? For example, oxidizing agents commonly used as chromium trioxide Cr2O7, chromium trioxide Cr2O3, chromium trioxide, or MnO2, or vanadium pentoxide, or MO2O3. So these are oxidizing agents. So I can use oxidizing agents at 500 degrees centigrade under pressure, say 10 bar pressure at 10 to 20 atmospheres. So under pressure, it is going to give benzene. I am going to write like this, benzene. So it is going to give benzene. How many carbons are there? 6. Very good. So it is going to cyclize like this, and these oxidizing agents are going to take up hydrogens. So how many? 1, 2, 3, 4, 5, 6. Right? So it 1, 2, 3, 4, 5, 6. 6 hydrogens will be removed to give this benzene. This benzene can be written as like this. Very soon I am going to explain what is aromatic compound and everything. So or it can be written as this. So aromatization of alkanes takes place using oxidizing agents. Oxidizing agents commonly used as chromium trioxide, vanadium pentoxide, and molybdenum trioxide. Under high temperature, alkanes undergo aromatization. Very good. Next, reaction with steam. So what is the importance of reaction with steam? Methane undergoes reaction with steam to give dihydrogen. So hydrogen industrially prepared, right? So before going to, yes, what we did, this is hexane, this is hexane. We have taken CH2, we did Cr2O3, heating, that is 500 degrees centigrades, at 10 to 20 atmosphere, we are going to get benzene. So this is benzene. Please write down. This is benzene. Alright, friends. So N-hexane gives benzene. And question to you: what has to be taken? Chromium trioxide, same reaction conditions, 10 to 20 atmosphere. If I want to make toluene, CH3 benzene, toluene. If I want to make toluene, what I have to take at left hand side? So hexane gives benzene. If I want to make toluene, what should I take? Yes, friends, any guess? So here 6 carbons are there, C6H14. Yes, here C6H6. Right. If I want to, here how many? C7, yes, H8. So what is the answer? Yes, think and write down in comment box. So what has to be taken? Yes, friends, to make toluene, what alkane, or what should I take? To make toluene by aromatization? Okay, write your answers in comments box. Right. At the end, I will give the answer. Right. Next, reaction with steam. Alkanes reaction with steam. Alkanes undergo reaction with steam and gives rise to hydrogen, methane. So what is steam? 2H2. H2O is steam. Yes, steam. In presence of nickel or some catalyst. This is a catalyst. Nickel. This is steam, not water. Steam means steam. How to make steam? Yes, water upon heating at high temperatures becomes steam. After 100 degrees centigrade heating, it boils and turns into steam. So alkanes reacting with steam gives rise to hydrogen. Yes, plus carbon monoxide. Carbon monoxide, 3H2. Yes, 3H2. This is bimolecular hydrogen. This is bimolecular hydrogen. H2 hydrogen is industrially very important reagent in reduction reactions. So industrial preparation of dihydrogen gas is prepared. Dihydrogen gas, this is gas, is prepared by reaction with steam. Reaction with steam. This is the reaction by which we can prepare dihydrogen gas. Dihydrogen gas is prepared by reaction with steam. Yes, friends? Yes. Next reaction, chemical reaction of alkanes. Pyrolysis. Pyrolysis is also known as cracking. So pyrolysis or cracking means alkanes undergoes pyrolysis to give lower alkanes or alkanes. For example, pyrolysis. If I take ethane, this is ethane. Yes, hydrogen. Pyrolysis. We are going to learn pyrolysis. This is also known as cracking. So alkanes undergoes pyrolysis. Pyrolysis is nothing but cracking. If I take ethane, it gives ethylene and breaking. It is breaking like anything. Cracking. So it is cracking. We can make it cracking. So what we have to do? Yes, heating is required under heating reaction condition. So this is high temperature. These alkanes undergoes cracking to give, for example, propane and methane. Different parts like it gives different lower alkanes or alkanes. So higher alkanes to lower alkanes can be prepared by cracking, by reaction of cracking. This is how you may expect the questions, right? So this is cracking. Alkanes, yes friends, till now what we have learned? Alkanes undergoes different types of reactions, that is substitution reactions, or mainly it is a halogenation reaction. Under halogenation I have covered chlorination, bromination and the ratios of products, that is primary, secondary, how much it is going to form. I have explained. Then nitration, sulfonation, chlorosulfonation. Yes friends, then today we have learned mainly combustion. We have learned combustion. Yes. Controlled oxidation. Yes. Then what else? We have aromatization, controlled oxidation, isomerization. Yes. Pyrolysis. Then very important topic of this alkanes is conformations. Very important. Yes, it is very important, required to all levels of chemistry students. Conformations. So what is conformation? Yes, conformations of alkanes. Conformers or conformations, it obtained by the spatial conformations of the compounds structurally different or isomers having same molecular formula, but the spatial arrangement of conformations. Please write down conformations. What is conformations? spatial arrangement of so spatial arrangement of atoms which can be, please write down, which can be, it is very very important, which can be converted into one another by rotating CC bond. Dear friends, spatial arrangements of the atoms which can be converted into one another by rotating CC bond gives conformers. Please write down conformers, or these are also known as rotamers. These are also known as conformations. This is very very important topic of alkanes for all levels of chemistry students, right? So spatial arrangement, these are isomers. What are isomers? Same molecular formula, but differ in structure or spatial arrangement. Differ in spatial arrangement of atoms. Spatial arrangement of atoms gives rise to conformers, rotamers, or conformations. Right? So this is very very important. Then why these conformations takes place? Because if I take ethane, for example, this is ethane. If I take ethane, so I am going to explain how to write these conformations. Yes. So this is the one conformation of ethane, right? It is known as eclipsed form of ethane. So when I see from here, this hydrogen and this hydrogen are on same line, right? These two hydrogens are same line. So because of same line, or the angle between these two hydrogens is 0, they will face torsional strain, right? So this torsion, to overcome this torsional strain, this is one carbon, this is one carbon, these can be rotated. So to overcome this torsional strain, it undergoes rotation, CC bond rotation, right? So what is the energy required for this CC bond rotation? Usually it is 10 to 20 kilojoules, even 1 to 20 kilojoules, it is very very easy, and this much energy is available at room temperature itself. So conformations, to overcome this torsional strain, it undergoes spatial rearrangement. So how? So the lower end I am going to same hydrogen and hydrogen, right? So here this hydrogen comes down, and this is the hydrogen, right? So which is here, this is, for example, I name it as 1, 2, not 2, this is 2, this is 3. So this is 1, this is 2, this is 3, right? Here this is one hydrogen, here it is one hydrogen. Then what is the angle? Yes, it is about 60 degrees, right? So the angle between this and this, it is about 60 degrees. Now it is staggered, it is known as staggered. Dear students, dear friends, dear children, yes, to overcome this torsional strain, alkanes undergo CC bond rotation, gives rise to conformers. It is very simple. Alkanes, to overcome torsional strain. What is torsional strain? Torsional strain is nothing but because of alignment of these atoms on same line gives rise to some strain. That strain is known as torsional strain. This torsional strain, or to overcome this torsional strain, undergoes CC bond rotation. Since for this CC bond rotation, the energy required is very limited or very small, so this CC bond rotation takes place even at room temperature. To overcome this torsional strain, it undergoes CC bond rotation to give conformers. This is staggered form. So spatial rearrangement of atoms which can be converted into one another by rotating CC bond gives conformations. These conformers are also known as rotamers or conformation. It is very important concept, conformations. So for all levels starting from KG to PG or from 10th class to PG level or even in with your PhD also, it is very important. Conformations are the compounds obtained by the CC bond rotation. These are conformations, right? So how to write conformations of ethane? For example, how to write conformations? Let us see conformations of ethane. So this is one conformation. It is known as eclipse form. This is staggered form. Then is this the only way to write? Yes, friends. There are two main ways are projections. There are two projections are known. One is Sawhorse projection. Please write down Sawhorse projection. Second one is Newman projection. So these two projections are very important in organic chemistry. So conformations can be written in the form of in Sawhorse projection. Sawhorse, Horse projection. Very important, students. Or Newman projection. Yes. So usually if I ask you to write ethane, how will you write? You will write C2H6, or you will write CH3 like this, or you may write CH3. So this way you may write usual way. In organic chemistry, if I ask you to write ethane, this is ethane C2H6 ethane. You may write in any of these forms. But to show these conformations, there are two ways to write ethane: Sawhorse projection and Newman projection. First one, Sawhorse projection. So there are some rules. Sawhorse projection. How to write? Yes. So what is CH3? For example, this is CH3. So this is ethane, right? So this is nothing but ethane. So the same thing has to be written like this. For example, this is backside or rear side carbon. This carbon should not be written C. No need to write dot also. Carbon. This is hydrogen. This is very important, students. This is hydrogen. For example, this is the carbon. Okay, this is the carbon. So here tilted line, you have to write some tilted line, not straight line. So this is the tilted line. This is how you have to start from this, and you have to write tilted line, some tilted line. Then you have to write 3 hydrogens, same as here. So same angle, right? This is Sawhorse projection. What is this Sawhorse projection? Sawhorse projection. So what is the angle between these two? This two and this two? It is 120 degrees. Is there any doubt? It is 120. Here also 120. But if you say this and this, what is the, I am looking from this side. This is front carbon, this is rear carbon. Rear or back side carbon. This is back and this is front. This is front. Front side, rear carbon or back side. So when I am looking from here, this hydrogen and this hydrogen is on same line, so they are eclipsed. These two hydrogens are eclipsed. So it is eclipsed. To when they are in eclipsed form, what it is the torsion known as strain, torsional strain. It will have some torsional strains. So to overcome that torsional strain, it undergoes CC bond rotation. So this CC bond is rotated. So what happens? Let us see. CC bond is rotated. I am going to keep this front carbon as it is. This is front carbon as it is. Yes. So I am going to, for example, for better understanding, I am going to give numbering 1, 2, 3. Right? So this hydrogen is going to be rotated. This hydrogen, so I am rotating like this. What happens? Let us see. So yes, hydrogen and hydrogen. So this is nothing but it is H1, this is 2, this is 3, right? So now how they are? They are staggered form. See, this is up, here one hydrogen is down, right? So they are like opposite side, and the hydrogen which was here, yes, it is going to have 60 degrees. It is going to have 60. What is the angle here? 120 degrees. But the torsional strain, there is no torsional strain. Staggered form. So this is Sawhorse projection. Sawhorse projection of ethane has to be written like this. So this is one carbon, You have to write carbon in a this way and hydrogens in a triangle form, and the angle between these two hydrogens must be intact, that is 120 degrees, 120, right? So here also 120 degrees, here also 120 degrees. The bond angle between hydrogens is not going to change. Yes, here also bond angle or bond length is not going to change. Here also bond angle or bond length is not going to change. What is the change? Yes, only rotation between CC bond is going to take place and going to give rotamers. Rotamers are conformations. Very important, friends. Formations, not confirmation, not I here, not I. Conformations are conformers. It is very important concept. So is this the only way to represent these conformers, Sawhorse projection? No. Another way, it is Newman projection. Staggered form. Right? Staggered form. This is highly stable. I will explain what is staggered form of Sawhorse projection. This is Sawhorse projection. Yes, Sawhorse projection. Next we are going to learn Newman projection. How to represent Newman projection? Yes, there is a way to write Newman projection. This is the front carbon. Yes, so based on this I am writing, and it is easy to understand. This is front carbon. This is front carbon. This is front carbon, and I am going to write hydrogens. What is the angle between these two hydrogens? These two hydrogens? Yes, 120 degrees. Very good. This is a front carbon. Then backside carbon has to be written like this. It is very important, friends. You have to write in a circle. Yes, make a circle. This is very very important. And the hydrogen which is here, yes, is here, yes, is here, backside hydrogen, and this is hydrogen. Newman projection of eclipsed ethane, eclipsed form ethane, eclipsed form of ethane, Newman projection. Yes, so this is nothing but eclipsed ethane, right? So this is the way you have to write eclipsed form of ethane. If I rotate, right? So if I rotate backside carbon, so what is the angle between these two, anything, it is going to be 120 degrees, right? So angle between two hydrogens or CC bond, it is not going to take place. Since this is torsional strain, it is torsional strain. To overcome this, it undergoes CC bond rotation, right? CC bond rotation gives rise to staggered form. So to write down the staggered form, the front carbon should not be changed, is not going to be changed. So Newman projection, torsional strain. There is no torsional strain in the here, no torsional strain. This is known as staggered form of ethane, Dear friends, dear children, it is very simple. Conformations are the compounds obtained by the spatial arrangement of atoms which can be converted into one another. This can be, suppose this is 1, if I say 1, this is 2, yes, it can be converted into both side, that is why I have given two-way arrow, both side, by CC rotation. What is the change? Here we are making some CC rotation, right? We are keeping this same in Sawhorse and Newman projection also. We are keeping the same. Simply we are rotating like this. We are rotating this CC bond. This is CC bond. We are rotating to give another form. These eclipsed and staggered forms are conformers. It is very very important, friends. Conformations. It is not conformations. It is conformations. Conformations can be written in Sawhorse projection form. This is Sawhorse projection or Newman projection. These projections are very 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 important to all chemistry students, organic chemistry students. These projections are used in organic reaction mechanism, right? So stereochemistry all depends on these projections. So please understand the concept at this level only, so that it will be easy at higher levels to understand stereochemistry and reaction mechanism. Right? This is front carbon, rear carbon, that is rear backside carbon, right? So this is the front carbon has to be written like this, and backside has to be written in a circular form, and backside upon rotation, yes. So the stability of conformers, it is very simple. You can explain which among these eclipsed form and staggered form, which is going to be more stable, staggered form is stable. Why? Because in eclipsed form there is a torsional strain. Here there is no torsional strain, it is stable, there is no torsional strain. And the angle, what I said, this is the angle. Here also, for example, what is the angle between these two? It is 60 degrees, right? 60 degrees, the angle between these two hydrogens is 60 degrees. This angle is known as, very very important, children, write down, dihedral angle. Write down, dihedral angle. So the dihedral angle of this is 60 degrees, then it is going to give staggered form, and this is stable. Whereas the dihedral angle of these two hydrogens is 0, right? So same line, 0 degrees. So dihedral angle at 0 degrees, it is eclipsed form. It is eclipsed form. So it is less stable. Less stable. To become more stable, this eclipsed form of ethane undergoes rotation, CC rotation, to give staggered form. Then is it easy to obtain this staggered form or isolate, or is it easy to isolate this top eclipsed form? Usually, practically, it is theoretically it is explained, but for ethane, yes, practically it is very easy to convert from one to another, that is from eclipse to staggered form. The energy required is only 2.5 kilojoules. It is very minimal. So it always turns from this to this to this. We may not get these two forms, but this is how eclipsed form and staggered form can be explained. And same way Newman projection also, eclipsed form and this is staggered form. Which is more stable? Staggered form is more stable. Staggered form is more stable because the dihedral angle. What is this? Dihedral angle. Please understand the concept. Dihedral angle is 60 degrees. It is more stable. Dear children, we have completed alkanes. Yes. So in alkanes, what we learned? It is very simple. What are alkanes? Introduction. What is the general formula of alkanes? CnH2n plus 2. Yes. This is general formula of alkanes. We have learned how to synthesize alkanes. Yes. What are the physical properties? What are the chemical properties? Under chemical properties, we studied halogenation. Under halogenation, we learned in detail about halogenation, that is substitution reactions. Under substitution reaction, we learned in detail about halogenation. Yes, chlorination, bromination, fluorination, iodination, and the ratios of primary, secondary, and tertiary halo compounds we learned in detail. Then nitration followed by sulfonation, chlorosulfonation also we learned. Today in this video we have learned about chemical properties of alkanes, combustion, right? Controlled oxidation, isomerization, aromatization, then reaction with steam, pyrolysis, right? So these are all the chemical reactions we have learned. The most important point in alkanes is conformations. Please understand the concepts. Conformations of the compounds which results by the spatial arrangement of there is nothing, we are not changing anything, both are same, but spatial arrangement. So that I will explain in detail when we cover stereochemistry. At this level, spatial arrangement of atoms results by rotation of CC bond is known as conformations. So it is not conformation, it is conformations. These are also known as conformers or rotamers. This is very important concept. Please, if you have any doubts regarding Sawhorse and Newman projection, please write in comment box. Even after this live session also, I am going to answer you. Your questions are welcome on this topic. Yes. So this is very important for all levels of organic chemistry students. Yes friends, thank you for watching this video. Please subscribe my channel Venus Academy for more updates on organic chemistry. We will meet again with new lecture, and next we are going to learn alkenes. Till then, bye. Sayonara. All the best. Enjoy. Arigatou gozaimasu.